So in the last lecture we discussed about how a fatigue crack grows, and a fatigue crack grows in several stages. So in the first stage the fatigue crack growth, so if there is an initial crack, it opens up and then there are slip bands which will be forming at an angle approximately 45 degrees to the applied stress condition, and so these two parts will open up, they will blunt, the crack will propagate by certain amount, and then the same, so while compression the whole thing will get compressed like this, so it will become similar to what was in the starting position, and the same cycle will be repeated over and over again in each cycle. So in each cycle you see these things which becomes the striation lines, because that will look like lines in 3 dimension, and that is the signature of fatigue crack propagation. So fatigue crack propagation, we learned that can happen also under the stresses which are smaller than the yield strength, and that is why we use fatigue cracking in order to create the sharp crack tip before fracture toughness testing. If you remember, we discussed that part also. So according to the theory of fracture toughness, so all that what we have studied on the crack tip stress definition. So we have studied the stress intensity factor parameter K, we have addressed the J integral parameter, and these two need the crack tip to be very sharp. So it wouldn't work, these two formulations will not be valid for a blunt crack. So you cannot have a hole as a crack in order to apply K and J. Although you can do it, but the formula which we have derived will not be applicable in that case. So we need a sharp crack, and we need a sharp crack in our CT specimen, compact tension specimen, before doing the test. Okay, right? So we use, to create this sharp crack, we apply some fatigue loading before doing the K1C fracture toughness test or J versus delta A test, which we studied in the fracture toughness chapter. So why we do this? Because we can do this kind of crack growth using cyclic loading under the stresses which are smaller than the yield strength of the material. So we will not be deforming the material plastically, and therefore we will not be changing the material's parameter to a very large extent. Of course we will have a very small plastic zone here, so a small area we are deforming which is not going to recover. So this is irreversible, the plastic deformation. So that we are doing anyways, but still, instead of just opening up in monotonic loading and creating a sharp crack, it's better than that, applying a fatigue crack growth. So that's an advantage of fatigue crack growth. Other than that, in the structural components and other things, fatigue crack growth actually is not an advantage. You want to avoid such situation where you have crack growth. So how do we define fatigue crack growth? How do we analyze that? So we can analyze fatigue crack growth by counting or by measuring the amount of crack which has increased. So let's say initially you had a length of A as a crack, so this length was A, and then in certain cycles of fatigue loading the crack grew by an amount of delta A. So this is the crack growth, delta A, and if that has taken, let's say, n number of cycles, then we want to find out that what is the crack growth per unit cycles. So that is called dA by dN. So A is the crack length and N is the number of cycles we are applying. So this can be related to the amplitude of stress with some power, some degree of that, and the initial crack length. So this kind of formulation has been suggested to describe the fatigue crack growth, but this will not describe the fatigue crack growth in the whole domain. So the fatigue crack growth behavior changes with increment in number of cycle and also with increment in the stresses. So it's a function of stress, and it's a function of course strain, because that's an effect of stress. And we have seen in the last lecture that we can define the whole range of fatigue SN diagram by the strain amplitude alone, right? So if you remember that part, we broke it into elastic strain and we broke it into the plastic strain amplitude, and for this part we had sigma f dash by 2 to n to the power b, that was Baskin's law, plus we had, so here we had E also because this is elastic, and here we had EF dash to n to the power C, which was our Coffin-Manson's law. So we can describe the whole fatigue life with the strain. So instead of relating the crack growth rate with the stress function, we can actually relate it simply to the strain function. So we can write dA by dN is equal to some constant C1, let's say, and strain to the power some constant M1. But we can have a formulation better than this one also. But to understand that part, we should look at the behavior of dA by dN as the stress intensity factor changes, because we know that once we have a crack in the system, the better parameter to describe the crack behavior is stress intensity parameter or J integral. That information we have from our concept of fracture toughness. So if we plot the crack growth rate dA by dN in log scale, so dA by dN if we plot on the y-axis, and if we plot the log of delta K instead of stress amplitude or strain, and in this case what will be delta K? Delta K will be K max minus K minimum, okay? And once we write in the form of K, we are making it very clear that there is a crack in the system. So we are talking about CT specimen kind of system. So we do have a pre-crack already. So this concept is applied on the structures, and we assume that we always have some cracks inside our structures, and that will lead to failure, and only then we can apply this. Okay. So in laboratory testing, we must have a pre-crack in our specimens to find out this plot, and in a structural component, from this we can do reverse calculation and find out that how much small of a crack in the system will not lead to a catastrophic fatigue failure. Okay. So that is what is called fail-safe design. So we know that it is going to fail, but we want to be safe. We want to be we want to have a possibility to predict that the failure will take this much amount of time. So that is what is fail-safe design. So we assume that there is a crack in the system. Once we have a crack, only then we can take the help of stress intensity factor. So delta K will be K max minus K min. What is K max? K max is the stress intensity which is achieved when we apply sigma max, right? So you know that we are applying either a stress variation or a strain variation. So we will achieve a sigma max and sigma min. So K max will be realized when we have the maximum value of stress in the system. So sigma max pi a, you can take the geometry factor alpha, which will not change for the second term, and so in the second term you will have sigma minimum root over pi a, right? So this becomes delta sigma, or this is also called sigma r, the range of stress, but I will write delta sigma, and delta sigma by 2 will be stress amplitude. So this amount is delta sigma and half of that is the amplitude. So delta sigma into alpha into root over pi a, this will be our delta k. Okay. So we are plotting log of delta k versus log of dA by dN, and when we do that, we find a plot which looks like this. So initially there will be no crack growth, then the crack growth is almost linear, and then it increases with a very high slope. Okay. So this behavior can be broken into 3 regions. So the first region, if I break it let's say till here, and then I break it till here and then rest. So this part is my region 1, this part is region 2, and this part is region 3. Okay. And this value where it is here, so this value is called delta k TH, meaning this is the threshold value of delta k. Below this there will be no crack growth. So if you apply a delta k which is lower than delta k TH, the crack will not grow. It doesn't mean that crack will not grow at all. We are talking about measurable quantity. So what happens in region 1 is that the crack is growing nanometers per cycle. So some nanometers in each cycle. So that is not measurable. Even if you measure it is not worth it. So therefore we ignore, so we assume that small amount of crack growth can be ignored. And so once you apply a delta k which is higher than delta k TH, only then there is significant amount of crack growth, and then the crack grows with increasing amount of delta k and follows a linear relationship in log scale. Okay. So it is a straight line in double log plot. And in the region 3, what happens is that crack becomes catastrophic. And usually in region 3 what happens is that this sigma max or k max, this k max reaches close to the fracture toughness of the material, K1C. So the meaning of this is that in the third region what is happening is that you are applying such a high stress, because we are increasing in the x-axis which is delta k, right? So what is happening is that you are applying such a high stress that the crack resistance of the material can no longer hold the crack driving force. So you are supplying too much energy to the crack to grow, and material cannot resist it because we have reached the fracture toughness of the material. And once we reach that, the crack is not going to stop. Okay? And these concepts are valid as long as we are talking about brittle material, because K1C is a concept which is valid in plane strain brittle materials. So very ductile material like aluminum and also a lot of steels, this tertiary part will have to have a different understanding, and instead of delta k we will have to deal with delta j, which comes from J integral. But overall the behavior will be same. So you only will have to replace delta k with delta j, but rest of the things are more or less going to be same. Alright. So the most important part of this curve is this linear range, because here we can apply fail-safe design. So here we can predict the crack growth is not that fast that we cannot do anything. Even though there is a crack in the system and we know about that there is a crack, So maybe by ultrasonic testing we know that our pressure vessel is having some amount of crack, or our railway wheel is having some amount of crack, or the rail track is having some crack. And because rail track undergoes a lot of fatigue cycle, because as and when the train moves from it, you apply a load, and when the train is passed, the load is taken away. So it reaches zero stress. So we are applying a cyclic loading on the track of the rails, and there, once we find out that there is a crack, we do have some time to replace it. Okay? Fatigue is also a concern in our aircrafts. So in aircrafts also, we, according to the protocols for the safety of the passengers, we can have for the safety of the passengers, we must replace a lot of parts, even if they do not have any damage, because we cannot take the risk. But rest of the parts we still can deal with them for some amount of time, as long as the crack doesn't become catastrophic. But in aircraft industries, this is not applied, because the risk is too high there. So the important part is this region, and in this region, the relation which governs the behavior of the fatigue can be described in this way. So dA by dN is equal to some constant into delta K to the power P. Okay? So if you take log of this, so log of dA by dN will become log of A plus P into log of delta K. Right? So we are plotting log of delta K and log of dA by dN. So the slope will become the exponent P, and we can find out log A by the intercept of this. Okay? So we can find these two values, and then we know what is happening here, and using this equation we can calculate the number of cycles required for an initial crack value so how many number of cycles will be required for the failure of the component, that we can calculate. So this equation, which describes the region 2, which is dA by dN is equal to A into delta K to the power P, is called Paris law. And Paris was the one who did a lot of experiments in this region, and this equation looks very simple. So, but finding out this and the application of this equation is very important, and it has become very, very famous. And Paris has died recently. I think he died in 2017. And but the application of this equation is very important, and I had the opportunity to meet Paris, but obviously he was very old, but it was a remarkable thing to meet somebody about whom you have read in the textbooks since you started doing engineering and all those things. So the application of this equation is very important, and so it was discovered, I think, in 60s, and now it is like 80 years, and the equation is still very important, and we still use it to find out the number of cycles required to failure. But before we do that, before we go in the detail of this equation, that how do we find out the number of cycles for failure, there are some variables which will be affecting this equation. So one variable is the value of sigma mean. So if you increase the value of sigma mean, then dA by dN increases in all three regions. Okay? So in all regions, the crack growth rate will increase if you increase sigma mean, and it makes sense. So the average value of stress at any point of time in the cyclic loading, you have increased that. So of course the damage is going to be increased permanently as long as you are applying cyclic loading, and your material is going to fail earlier, meaning that your crack growth rate will increase in all the three regions. Okay. Apart from that, if you change R value, so R value is the ratio of sigma min and sigma max, which becomes also the ratio of K min and K max. So if you increase R value, then what will happen? So K max, so if you increase R value, then K minimum will be R times of K max, and if you are increasing this factor, it means that you are increasing the value of the minimum stress. Okay. So the effect of increasing R is less in region 2 in comparison to region 1 and region 3. So what is region 3? If you remember this plot, so it was something like this. So this was region 1, and this is region 2, and this is region 3. Okay. So the effect of increasing R is more in region 1 and region 3. So region 1 is the part where fatigue crack is initiating, and that usually takes the maximum amount of time in a fatigue test. So when you do not have a crack initiation part will take huge amount of time. So usually it takes 80 to 90% of the total time of failure in crack initiation if you do not have the crack already in the system. But if you do have the crack in the system, then the starting of propagation, that part has more effect if you increase the R ratio. So it will become easier for crack to start growing if you increase the R ratio, and also the catastrophic failure will be much easier because my sigma minimum or K minimum, so my lowest amount of stress intensity factor is much higher if I am increasing R value, right. But the effect of that on the second part is not very high. Okay. So apart from that, there is another important thing on Paris law and also on fatigue, is that the concept of delta K has a speciality. So if your sigma minimum is negative, okay, so if it is less than 0, so you are going in compression, then there is no definition for K. K will not work in compression because crack is closed. You have a crack, right, and then you apply compression, so crack gets closed, so there is no possibility of the stress intensification there, right. So K is undefined when you have compression. So if you have a stress cycle which goes from tension to compression, meaning that your sigma mean is 0, so you are going from sigma max to sigma min, which is in compression. Sigma minimum is compression, sigma maximum is in tension. In this case, how do we calculate delta K? So delta K was sigma max into root over pi a minus sigma minimum into root over pi a, right. But sigma minimum is negative, so this will add up to double, but that is not the reality. In compression, the crack is not going to feel anything, no stress intensification. So in that case, what we do is we replace sigma minimum with 0. Okay, so we end it here, the delta K concept. So then it will become just sigma max root pi a will be the value of delta K. Okay, so this is very important. Now once we have understood this, the effect of R on Paris law can be described by this equation, which is you just have the simple Paris law, and then you have a factor which decreases the amount of crack growth minus delta K. Okay. So if you take the denominator on the left hand side, that defines a factor which says that, or you can break it down to understand something. So let us break it down. So dA by dN is equal to A into delta K to the power P divided by, and 1 minus R is K minimum by K max, so that will become K max minus K minimum divided by K minimum, K max, yeah, into Kc minus delta K. Kc is the fracture toughness, okay. So we do not know if we are doing it in mode 1 or mode 2. If it is in mode 1, it will be K1C, okay. So this is what it will be, right, and then that becomes equal to A into delta K to the power P divided by, so K max minus K min becomes delta K, and delta K is also on the other side, so we can take that part common, right, and then it becomes K1C by K max minus 1, right, okay. And now we take it on the, so what is happening, so here also it is very clear. So the effect of R actually is reciprocated in this way, and what are we seeing here is that this factor defines that how much your K max is in comparison to the fracture toughness of the material, okay. So we can further break it, so this will be K1C minus K max divided by K max. So that numerator K1C minus K max will tell you that how far away you are from the fracture toughness of the material. Fracture toughness is the K1C in monotonic loading, right. So how much far away you are from that value describes the effect on the crack growth rate, right. So if you are further apart, then the crack growth rate should decrease, and if you are very close to K1C, then this should increase. So you see, when this value will always be greater than 1, right, because K max at most can reach the fracture toughness value. You cannot go beyond that, because once you reach K1C, it is going to propagate anyways in monotonic loading, and we are talking about cyclic loading. So K max usually is less than K1C, and this factor is always greater than 1, right. If it is 1.0001, then that value is very close to 1. So crack growth rate is not having any effect. But if that value is 1.2, that means you have a very high effect on the crack growth rate, okay. So that's how the effect of R is demonstrated on Paris law, okay. So this part is clear. And now we will deal with the calculation of number of failure cycles for a given amount of crack length using Paris law in the next page. So how are we going to calculate? So let us start with the Paris law. dA by dN is equal to some constant into the delta of stress intensity factor to the power P. This is the law which is being followed in the second region of the fatigue crack growth diagram. So remember that when you do not have a crack initially, then we follow SN diagram. When we have a crack, then we follow dA by dN versus delta K plot. Okay, so that difference should be very clear in your mind, that there are two cases. One, we have no crack in the system, so then we simply talk about fatigue. Once we have a crack in the system and we are applying cyclic loading, we are talking about fatigue crack growth. Okay, and these two have different laws and different scenarios, because in one scenario we include the part of crack initiation, in the other part we do not include that part because we already have a crack in the system. Fine. So now what will be the final crack beyond which the material will not take any load and it will just propagate? What will be that critical value of crack after which the fracture becomes very, very easy? Can we calculate it? So for that we need to find out what is the critical value of a stress intensity factor. Once that has been applied, the material will simply break, and that value we know is the fracture toughness of the material. If we are dealing in mode 1, I will write K1C. If we do not know what mode it is, we can just write Kc. Depending upon the mode, it will be K1C, K2C, K3C, or it can be a mixed mode. So, but to make it simple, we will deal with mode 1. Why do we deal with mode 1? Because mode 1 is the conservative approach, meaning that mode 1 is the worst scenario. So, if we are safe in mode 1, we are safe in all other scenarios as well. This is why K1C is more important than others, because that is the worst case scenario as long as safety of the structure is concerned. So K1C is the value at which the crack length will reach its critical value. So K1C should be alpha into sigma into root over pi a c, which is the critical crack length. Now from this equation I can calculate what is AC, right? So from this equation I am calculating AC, which will be equal to K1C whole square divided by alpha square sigma square into pi. Okay, so this is my final crack length. Alright, beyond which I don't need any more load for material to fracture. Okay, and we start with a crack which has an initial value. So we start with finite value of crack, which is, let's say, AI. Okay, it could be 5 mm, 10 mm, depending upon what component or specimen we are dealing with. So let us say that we start with AI value and we reach this value, and that's the end of it. Okay, so now if we break this equation, then dA by dN will be equal to A into, and delta K we can break using again similar formula. So that will be K max minus K min, right? So, and K max minus K min we can break in sigma terms. So we will have sigma max root over pi A. Let us keep it A for now, and alpha will be there minus alpha into sigma minimum root over pi A, and this to the power P. Okay, so this becomes A into, everything else is constant, so we can common, so we can take that out. So alpha to the power P, and then pi into A to the power P by 2, and then delta sigma to the power P by 2, right? So this is what we have as dA by dN. Okay, so now I will take A on this side, so I will have dA divided by, so I can simply take just A part and pi I can keep it there,